Hi, today we're going to learn about exponential functions and logarithms, and this is under college algebra review. So in this section, I will graph exponential and logarithm functions, and I will use the properties of logarithm to find x and expand as much as possible, and also I will use the compound interest formula to find time. So let's get started. So the first one is an exponential graph. It says we must graph the f of x equals 3x plus 1. Before I go any further about graphing exponential graph, I want to go over some properties of exponential graphs. So the properties are the rules of exponential graph of f of x equals a of x. The function is f is increasing for a is greater than 1 and decreasing for if a is greater than 0 and less than 1. So basically, if it's less than 0 but still positive, it's decreasing. And I'll go over this when we graph it, and this will probably make all sense when we graph it. So, and then y-intercept is from 0 to 1. It has a horizontal asymptote on the x-axis, and the range is from 0 to positive infinity, and the function is 1 to 1. So this probably don't make sense now, but when we graph it, so we have a y equals 3x plus 1. So what is our a? Our a is this 3, right? So if it's greater than 1, it means it's increasing, right? Let's go back. Yes, if it's greater than 1, it's decreasing. I mean, it's increasing. Okay, and what else? It has also this one right here means we have a vertical shift. I should do a section where we have to do like shifting and phase shifting. I probably will do it. For right now. Okay, so what else do we need to know? We know so a is increasing. So here's a typical exponential graph, right? It always has a y-intercept of 0, 1. So this is 0, 1. So this could be y equals e to the x, or y equals 2 to the x, right? Because it's greater than 1, because the a is 1. So it always has y-intercept of 0, 1, and notice how here's your x and here's your y. Notice how it never it gets really close to the x-axis, but it never touches. So that's why we have a horizontal. Yeah, it has a horizontal asymptote on the x-axis. So it has a horizontal asymptote on the x-axis, and it's definitely 1 to 1 because if you do the vertical line test, it passes. It only hits the point 1, hits it once. And the range is from 0 to positive infinity. Let's see if that's true. Let's look. The range is the y value, so yes, it gets really close to 0, and then it just increases. So that's true, 0 to positive infinity. So yes, we done that. So okay, good. So this is what your typical exponential function. The difference is we have a phase shift. So our graph is going to look something like this now, because not a phase shift, a vertical shift. So it will look something like this. Instead of the y-intercept of 0, 1, it's going to be 0, 2, right? But it has the same style of the exponential of this e to the x graph. But the only difference is the y-intercept is a little different. It's our y-intercept is 0, 2. So it's going to look something like this. So this is your y equals 3 to the x plus 1. So it kind of looks like this one, but the only difference is there's a vertical shift. So the y-intercept is 0, 2. And yeah, that's pretty much it for exponential graphs. And I'll probably do a section under college, just regular college algebra of graphing exponential and logarithm, because I really want you guys to understand like graph. Okay. That's a problem. Okay, so what about, let me give you another one. I'm going to clear. What about the graph of, this is 2, g of x equals 2x minus 1. Now this looks weird because of this weird x to the negative 1, right? That looks kind of weird. But don't worry, we'll just break it down into 2 graphs. So let's graph g to the, g of gx is the same thing as y. Let's graph y to the 2 to the x, right? Let's graph this one. Okay, so we know that a is greater than 1. Our a is 2, right? And it's greater than 1, so it's definitely increasing. And we know that it has a y-intercept because all exponential has a y-intercept of 0, 1. So let's go right here, and this is 0, 1. And we know it's increasing, so it's going to go something like this. Oh, that was awful. You can actually make a data chart table where you plug in points to make it look more nicer, but this is just like pretty much a rough estimate. Okay, so 0, 1. So this is y equals 2 to the x, right? But we need, I think there's a phase shift on the x-axis, because I'll show you. So the graph of y there's going to be a phase shift. So here's 0, 1. This is 1. It's going to be, there's going to be a phase shift on the x-axis of 1, because what you can do is you can set x minus 1 equals 0 plus 1. So there's a phase shift on the x-axis on 1. So we're going to have to move on the x-axis one value. So instead of 0, 1, it's going to be right here, which is 1, 1. And then it's going to make that U shape, right? Because it's increasing. And it never passes the x-axis because that is our horizontal asymptote. Yep. And that's how you graph this y equals 2 to the x minus 1. Okay, number 3. Okay, it says express 8 negative 2 equals 1 over 1/64 in logarithmic form. So I'm going to use this rule, and I think I wrote it a few times, but I'll just write it again. Y equals log base a times x if and only if a to the y equals x. So we need to put it in. So we need to put it in. I think it's in this form, right? It's in this form. So we got to put it in this form because we want it in logarithmic form. So this looks like this. So what would our a be? Our a would be 8, right? And our y is -2. And our x is this whole thing, 1/64. So if we found our a, y, and x, we have to put it in this form. Y equals log base a to log base a times x. So y is -2 equals log base, our a is 8, log base 8, and our x is this whole thing, 1/64. And you can actually put it, if you don't, you could put the -2 on the right, it's still the same answer, right? So this is our final answer. Let me do a next one. I'm going to actually try to erase it because I still need, for the next problem, I'm still going to use this rule. Sorry if it's taking too long, but I just don't want to erase the whole board. I think that's good enough. Okay, number 4. Same rule. So we have 5 square. Whoops. Sorry. I'm just going to erase the board, sorry. So number 4, we are given 5 square equals 25. And then we have, I'm going to write it again, log base a. If and only if a to the y equals x. Okay, so same rule, we got to put it in logarithmic form. So let's find our, so 5 squared equals 25 looks like this, a to the y equals x. So we just got to figure out what's our a. Our a is 5, and our y is 2, and our x is 25. So we just got to put it in this form. So y is 2 equals log, and then our base is, our a is our base, which is 5, and then our x is 25. And that's your final answer. Let me erase. This time I hope I don't have to clear the board. Actually, can you guys remember this rule? I'm gonna have to erase the whole board again. So the next problem is number 5. Log base 2 to the x equals 4. If you remember the rule, so we gotta this time we're not gonna put it, we're gonna do the opposite. So we gotta do the a to the y equals x, right? So we know that our a is 2 and our y is 4 and our x is just x equals x. So a to the y, so 2 to the 4 equals 16. I mean 2 to the 4th equals, sorry, x. So but 2 to the 4th is 16 and 16 equals x. Number 6, we have log base x to the 9 equals 2. So the same thing like the last problem, we got to figure out what is our a and what is our y. So our a is, the base is x, our y is 2, and our x is 9. So we got to put it in a to the y equals x form. So x to the x to the square equals 9. And then we're going to take the square root of both sides. X equals positive 3 and negative 3. We're going to get two answers. The reason why we can cancel negative 3 is because you cannot have a negative as a base, right? So we can't. We'll try negative. Let's check if 3 works. So log. I'm gonna plug in 3 into x. So log 3 equals 2. So is this true? 3 to the square equals 9. Definitely true, right? 3 squared is 9 over 9. 9 equals 9. So our answer is x equals 3. And let's do number 7. So now we're graphing log graphs. Okay, so if you don't know, log graphs and exponential graphs are practically inverses. So I'm just quickly going to go over some of the properties of log graphs. So the properties of log graph is that the function f is increasing for a is greater than 1 and decreasing for when a is greater than 0 and less than 1, so it has to be positive. It has an x-intercept of 1, 0, has a vertical asymptote on the y-axis. The domain is from 0 to positive infinity and ranges from negative infinity to positive infinity, or all real numbers, and it's one-to-one function. So let me show you what I mean by inverses. So remember 0, 1 was our y-intercept for the function of the exponential. So this is this could be y equals 2 to the x. Right, this is your typical exponential graph, has a y-intercept of 0, 1. Now our log graph, when it's greater than 1, it has an x-intercept of 1, 0. See, see how their inverses, how they switch the x and y value? So this was 0, 1, now it's 1, 0, and now it's just an x-intercept. So it's going to look something like this. Oh gosh. It's never going to touch though, it's never going to cross the y-axis. So this graph looks something like, this could be log base 2 times x, right? See what I mean by inverses? They have it, just their whole x and y's are opposite. This has a y-intercept and now this has an x-intercept. So that's what I mean by inverses. So let's graph log base 3. So log base 3 is going to look something like this. Here's your x and here's your y. Always make sure you label it. So our a is 3, which means it's increasing. So it's going to look something like this, right? It's almost going to look something like this. Actually, it is exactly, but since there's no plus 1 or negative x minus 1, right? There's no phase shift or vertical shift, so that's why it's going to look something like this. So this is 1, 0, has an x-intercept of 1, 0. So, and make sure you label the graph y. This is y equals log base 3 to the x. So let's go back to the rules of logs. So let's look at this and then so it says it has a one-to-one function, right? That's true, right? Because if you put a line through it, it passes the vertical line test. It has an x-intercept of 1, 0, yes. Yes, right here. It has a domain, so it has a domain of 0 to positive infinity and range of all real numbers. So let's look at that. So the domain is the x value, right? It gets really close to the y-axis, but it never touches, so that's why it starts from 0. And then it just goes, it increases. That's why it's positive infinity. Now let's look at the range. Remember, the range is the y value, so as you go down this graph, it keeps going, and the value just keeps on going negative. What about when you go positive on the y value? As you increase, the y value increases. That's why it's positive infinity, or all real numbers. And it has a vertical asymptote on the y-axis. Yes, that's true, because look, it gets really close to the y-axis, but it never touches, and so that is like a vertical asymptote. Okay, what do I mean? What happens if it's decreasing? Like let's say we had a problem that was decreasing. Let's say we had a y equals, I don't know, log base 1/3 x. It's less than 1 but greater than 0 or positive, so it's going to look something like this. It still has an x-intercept of 1, 0, right? And then what happens is it's like a weird reflection. So it's going to look something like this. So this is your typical y equals log. This is when it's decreasing. So this is a decreasing log graph. And I will probably do a whole section on graphing log under just regular college algebra. Okay, next problem. Okay, so number 8 says use properties of logarithms to expand as much as possible of log base 4 3 divided by y. So what do we know about division? We're dividing, right? So basically we're going to break this into 2 logs. That's why expand means make it bigger. So what happens when you're dividing for the log rule? When you're dividing, you're really subtracting, right? So let's break this into 2. So it's going to be log base 4 of 3 minus log base 4 of y. And that's probably the most simplified, that is probably the most expanded form you can get, because I don't see any exponents. So this should be your final answer. And then the last one is, it's a word problem, so we're going to use compound interest. We're going to use compound interest. So it says, how long will it take for 850 to be worth 1,000 if it is invested at a 12% interest compounded quarterly? So we're going to use the compound interest formula, which is A equals 1 plus R over N times N times T. So we got to find T. First off, what is A? A is the amount. Oops, forgot the P. Silly me. So it's A equals P times 1 plus R over N raised to the N times T power. So A is amount, P is principal, R is rate, and then N is number of compounds. Number of compound per year. So what that means is, like, is it compounded yearly, monthly, quarterly, etc. And T is number of years. So let's use what we have. So we said that our A should be 1,000, right? Our principal is 1,000. Our amount is 1,000. And then our P is 850. Okay, now what is our rate? We said its rate is 12%, but we want it in decimal form, so we have to move it 2 places to the left. So our rate is 0.112. 0.112 divided by N, which is the number of compounded years. So it says compounded quarterly. So our N is 4, because quarterly means 4. And then for our N, so we have to raise it to the N times T, so it's 4T. We don't know what T is, so that's why we put T. So how long? The question says how long. So we gotta find T. So how are we gonna do this? First off, I'm gonna get rid of this 850. So I'm gonna divide both sides by 850. This becomes a 1, not a 0, just 1. So, and then 1,000 over 850 is, we could get rid of these zeros, and it could be reduced by 5, so this should be 20 over 17 equals 1 plus 0.112 over 4. Okay, so our goal is to find t. So what are we going to, how do we do this? Alright, this looks like a log problem. So to bring down this 4t, I'm going to have to take logs of both sides. So this should be 4t log of this whole thing, 1 plus 0.112 over 4. And then you have to do it on the left side. So it should be log of 20 over 17. Good. So now I want to solve for t. So what I'm going to do is I'm going to divide this by log of this whole thing and then divide it by 4 as well. So if I did that, I'm going to divide. So I'm going to divide 4 log 1 plus 0.112 over 4. So our t is this, is log 20 over 17 for log and if you were to put it in the calculator, I get t equals 1. So our answer could be this one or this one. And that's it for this section.